So in this practice problem, we've got an arrangement of these three charges forming an equilateral triangle. And we specifically want to know what's the electric field at this location. Because we're later going to be putting a small negatively charged particle there and figure out what happens to it. But to start with, we just want to know what's the electric field at that location. So that means we should be investigating the electric field contribution from each of these charges. Let's say we call these charges A, B, and C. So what would be the electric field contribution caused by A?
It would go down, right, from the particle?
Right, because this charge is emitting or creating electric field outwards in all directions. At this one location, outwards means downwards. So this would be the electric field contribution caused by source charge A. And then source charge B creates electric field in which direction?
Upwards.
Yeah. At this location, that would be upwards. So that's electric field contribution from B. And then charge C is negative. So what's that going to do?
It would go to the right, right?
Right, because that would be towards that source charge. And we can't necessarily say anything about magnitude here. It looks like this charge is a little bit further away than the other ones are, but we also don't really have any information about how strong those charges are. So we can't really say for sure exactly how strong these electric field contributions are going to be. But to find the net electric field at that location, what would we do with those three vectors?
I know that electric fields for B and A would cancel out, and then we would just be left with C, I believe.
At least if we're assuming A and B are the same amount of charge. I don't think the problem specifically says that, so we don't know for sure that A and B are going to be the same strength electric field, but they're going to at least partially cancel out. We've got EA plus EB plus EC. EA and EB will at least partially cancel out. We might have a little bit of upness or a little bit of downness, but we're definitely going to have a quantity to the right with nothing to cancel it out. So we might have to the right, or to the right and a little bit up, or to the right and a little bit down. But we know it's at least going to have a positive X component. We don't know for sure about the Y component. Any questions on that so far?
Casey, quick question. So like it says like the point's like halfway between the two charges for the positive. So couldn't they technically be the same magnitude? Or is it because we don't know what the charge magnitude is?
Exactly.
Okay.
They're the same. This location of interest is the same distance from both these particles. So that's definitely going to be the same. But we don't know for sure what the charges are. If we do assume that all these charges are the same amount of charge, then yes, the EA and EB will cancel out.
Okay.
If we don't know for sure what the charges are, we don't know how strong these magnitudes are.
Got it.
So they might or might not cancel out. But assuming that they are the same amount of charge, then EA and EB will cancel out. So we just get EC to the right is the total electric field. But either way, we know the electric field is at least somewhat to the right and maybe a little bit up or down. Any questions on that so far? And then what we're going to do is we're going to put a negative test charge there. So at this location, we're now going to insert a negative test charge, negative little q. And at this point, we don't really need to care about the source charges at all anymore. We know that at this location, the electric field is to the right. That electric field is to the right, maybe a little bit up or a little bit down. We don't know for sure yet. So what does that tell us about the force on this particle?
It would go left.
Yeah, we're going to get a force to the left and maybe a little bit down or up, but it's going to be just in the opposite direction of that charge, because how are force and electric field related to each other?
Force is equal to Q times the electric force.
Right, or electric field, I would say.
Oh, yeah, sorry.
So the electric field is to the right, but we're multiplying by a negative charge. If you multiply a vector by a negative scalar, you get a vector in the opposite direction. So the force on this object is going to be in the opposite direction. So the force on the test charge is definitely going to be to the left, maybe a little bit up or down. And at that point, it's going to be direction of the force. So it's going to start moving in that direction then, because the force causes acceleration. At this location, assuming we just put it there at rest, the force is going to cause it to start to move. Once it's moving, the force causes it to get faster and faster and faster, because force causes acceleration. Force causes a change to velocity. Any questions on that so far? And let's see what happens as it gets further away, though. Let's say we allow this particle to drift for a little while and then reanalyze what the forces are. Because we know this particle is going to experience a force to the left, so it's going to accelerate to the left. But we want to know, does it go forever in that direction? Does it get faster and faster or slower and slower? Does it ever come to a stop? So let's analyze what's happening a little bit further to the left. If we consider some point over here, let's say right here, now let's figure out what the electric fields are going to be. You're going to get electric field from A pointing in which direction?
It's like to the left downwards, if that makes sense. Downwards
The
left.
electric field from A? Not the force, the electric field. Oh wait, no, you're right, because it is a positive charge, right?
Yeah.
Sorry about that. Yeah, the electric field is going to be down and to the left because we should expect electric field away from A. And it's going to be somewhat weaker because we're further away. And what about electric field from B at this location?
Upwards left.
Up and to the left. And again, somewhat weaker because we're further away. For simplicity, let's assume A and B are the same charge. There might be a little bit more up or a little bit more down if they're not the same charge, but for simplicity, let's assume they are. And then C creates electric field in which direction?
To the right.
To the right. Although note that we're now a lot further away from C, so what does that tell you?
It's like the magnitude is kind of smaller now for the electric
field. We have a small magnitude electric field contribution to the right. So now we're going to add these three electric field vectors together. We've got electric field from A plus electric field from B plus electric field from C. When we add those, what would you expect to happen?
So for A and B, would the would the Y components cancel out, but the X components add up?
Yeah, I think components is a great way to look at this. If we look at these in terms of X and Y components, if you look at just the Y components, we got upwards and downwards. So those are going to cancel out, again, assuming that these are the same magnitude. But the Y components or the X components are going to combine. So these together result in a large vector to the left, plus a small vector to the right. So what's going to happen there? The result is going to be in which direction?
More towards the left?
Yeah. It's partially canceling out, but we still end up with electric field to the left. So we're going to get an electric field to the left in total there. You could also do this by adding them head to tail. If you've got from this point, EA plus EB plus EC. And the total electric field is going to be from the original starting point to the final ending point. So this still suggests that the net electric field is to the left. Any questions on that electric field so far? So we know at this location, the electric field is to the left. How does that compare to what it was in the original location?
It's the opposite side.
In the middle here, we had electric field to the right, but now over here, we have electric field to the left. So let's see what happens if we put the particle there. We've got this small negative test charge at this location. It was already moving to the left because of the original electric field. But at this point, you've got a negative charge goes into the left pointing electric field. Which direction is the force on it?
To the right.
We get a force pushing back to the right.
So this problem is basically saying that the particle will, like if it's at the center of all three of them, it will go to the left and then it'll stop and it'll go back to the right and cycle like that?
Exactly. We should expect oscillation here because as it moves to the left, it gets a force to the right, which makes it, and of course that doesn't make it immediately change direction. Force doesn't cause motion. Force causes gradual change in motion. So as it's moving to the left, but getting a force to the right, it's going to start slowing down, perhaps eventually come to a stop and get pulled back, getting faster and faster. But then as it gets to some point over here, it's going to get slower and slower, come to a stop, bounce back. We can expect oscillation here if the energy is low enough. Just like the oscillators we were looking at in 7a, if you have a high enough energy, it may be able to escape. It may become unbonded. But if you've got low energy, you're going to get oscillation in this bonded state. Any questions on that so far?
Just to clarify, the direction that the force is facing is the direction of the way that like the molecule or the charge is moving, right?
Not necessarily. The direction of the force is going to be the direction of the acceleration, because force causes acceleration. In this case, we were assuming the particle had started moving to the left. Mm-hmm. At this point, maybe it's still moving to the left, but it's experiencing a force to the right. So if a particle is moving in one direction, but experiencing a force in the opposite direction, what's going to happen?
Won't it gradually move towards the opposite direction?
Eventually, maybe. At the very beginning, though, I think we can just expect it's going to slow down. Okay. You've got an object moving to the left, but experiencing a force to the right. That force causes acceleration, which is going to make it slow down. Acceleration in a direction opposite the velocity means the particle gets slower and slower. If it lasts long enough, the particle will eventually come to a stop and then start moving in the other direction. Okay. But all we can say for sure at this instant is that the particle is in the process of slowing down.
Okay, so how is it then that in the beginning when we had the charge right in between the two positive charges, mm-hmm. we said, okay, now the charge is moving to the left. How did we know it was moving to the left when it could have just been moving to the right still, but just slowed down?
I think the problem did say we put it at rest. Did I say that somewhere? It says it starts from the point exactly halfway between the two charges and is free to move. I would interpret that as meaning it's not moving yet, but it is able to start moving.
Okay.
So if we put the object in the center at rest and just let go, then the force is going to make it start moving. And since the force was to the left, the object starts moving to the left.
Okay, that makes sense.
And gets faster and faster. At some point, we now have a force to the right. So that's going to make it slow down. If the force lasts long enough, eventually it comes to a stop and then starts moving backwards.
Got it. Thank you.
Mm-hmm.
Casey, sorry, I had a question. I thought the original, like when it was close to it, the
sorry, is it possible for you to speak a little louder? I'm having difficulty hearing.
Can you hear me now?
Yeah, go ahead. Thanks.
I'm a little confused because I thought for earlier, like for part A, the electric net, like the electric field was going to the right. I thought it was going to the right, so it would cancel out.
Yes, at the beginning when we were in this location, the electric field was pointing to the right. So at this original location, directly halfway between A and B, we did have the total electric field pointing to the right because the up and down from A and B canceled out.
Yeah.
So we have that.
Oh, but now that we've moved it further, now it's moving to the left.
Exactly. The electric field over here is to the left. Because keep in mind, electric field is a property of location. If you're at a different location, you could get a different electric field strength and different direction.
Okay, got you. Thank you.
Mm-hmm. In fact, if we were to map out the electric field in various different locations, I'm not sure exactly what it's going to look like for a 3-charge arrangement, but presumably if it's to the right at this location and to the left at this location, there's going to be some location in between where it happens to cancel out exactly. There's going to be some spot where the leftwards contributions from A and B and the rightwards contribution from C happen to cancel out. That would be a location where the electric field is 0, which means the force on the particle is 0, and that means that would be our equilibrium location. Just like for the spring oscillator or the Lennard-Jones potential oscillator back in 7A, the object oscillates around an equilibrium point in the middle where the force is 0. If we can find a location where the electric field is 0, that means that's going to be the equilibrium location for that particle. So it's going to oscillate, if it's oscillating, it's going to oscillate around that point. But if it has enough energy, it may be able to break out of the bond entirely, because we know, what do we know about electric forces if you get further and further away?
They get weaker.
Right. So if the particle is, let's say you put the particle here and give it a push. If it's already in motion, if it's moving fast enough, it is going to slow down because of the attractive force. But if it's moving fast enough, then it's not going to slow down enough to come to a stop. And as the force gets weaker, it just keeps moving further and further away. So it's possible in this case for the bond to be broken if the particle has enough energy to start with, if the particle is moving fast enough to start with.
But so for the motion of the particle, would it be okay for us to just say that it's like gonna go left and right around the equilibrium point? Does it slow down and stop at the equilibrium point, or?
Equilibrium isn't where it comes to a stop, because remember, equilibrium is where there's no force. So if it's moving and it's passing through equilibrium, at equilibrium, it's briefly just going to move with a constant speed, not slowing down at all. So as it's approaching equilibrium, it's getting faster and faster and faster and faster, and then after equilibrium, it's going to get slower and slower and slower and slower. It's almost as if the particle is being attracted towards the equilibrium point.
So it constantly oscillates around that.
Yeah. Yeah, I would expect, if we just put it here and release it from rest, I'd expect oscillation centered around the equilibrium point. It's not necessarily going to be completely symmetric though, because this is not a symmetric arrangement of charges around the equilibrium point. So maybe it's going to be going, I don't know, just as a wild guess, maybe like zipping in really fast here, and then spending more time lazily drifting out here, gradually bouncing back. So it might be oscillating kind of like that.
Oh, but it never like stops at the equilibrium point then?
Right. The only time it would actually come to a stop at the equilibrium point is if there's some sort of friction or air resistance so that it's gradually losing energy. If it's gradually losing energy, then it's going to oscillate smaller and smaller and smaller and smaller, and eventually settle down on the equilibrium point at rest. But if it's in motion, it's never going to be stopping at the equilibrium point. In fact, it's going to be going through equilibrium at highest speed and stopping at the turnaround points, Rmin and Rmax, on the outer edges of the oscillation. Just like
So are we supposed to assume that there is no friction? I don't think the problem mentions that.
Yeah, the problem doesn't say anything about friction. It doesn't say there's any sort of energy loss. So in a system like this, I would assume it would just keep oscillating forever.
All right, cool. Thank you.
Mm-hmm. Any other questions on that one? All right, then let me see if I can track down some problems on quantum stuff, because there were several questions on that. Does this one have any good quantum problems? Yeah, actually, let's take a look at maybe 5 and 6 from this one. Because it looks like those are both about the quantum energy stuff. So here we've got neon, nuclear charge Z equals 10. We want to know the energy difference between the lowest energy levels. If we're talking about an atom, what formula could we use for the energy levels? Anyone happen to have a formula for that? It's listed on here. We got there we go. Atomic energy levels, Z squared times 13.6 over N squared electron volts. So that should be the formula we can use formally for hydrogen-like atoms. Basically small atoms that for whatever reason have only one electron. This one might not have only one electron, but I think we can treat it as if it does for simplicity. Was that Z or Z squared? Z squared. So negative 13 points electron volts times Z squared over N squared. And that'll tell you the energy of the nth level. Because remember, for very small energy systems on the molecular level, energy only comes in these specific values and nowhere in between. By plugging in whole numbers for n, 1, 2, 3, 4, 5, et cetera, we can find the possible energy values. So let's try that. If we just start listing out energy values, first of all, what's Z going to be here?
Sorry, I have a question.
Mm-hmm.
How did you know that this was the hydrogen-like atom formula?
Well, we know it's at least an atom. And the only formulas we really have at this point for quantum energy levels are the hydrogen-like atom, the oscillator, and the electron in a one-dimensional box. So if we want to pick the one of those formulas that most closely corresponds to this case, this is definitely not an electron in a one-dimensional box because the atom is not just one-dimensional. We also aren't talking about an oscillator because an oscillator would be more like two atoms that are oscillating back and forth because they're being attracted and repelled. So
so like with a bond or something?
Yeah, exactly. In fact, that's basically the quantum treatment. The quantum harmonic oscillator is essentially the quantum treatment of the bonded particles, the particle model of bond energy that we were looking at back in 7A. But this one isn't either of those cases. This is just an atom. We're looking at the possible energy levels of one atom. So it may not truly be hydrogen-like, but we can treat it as being close to hydrogen for the approximation at least.
Okay.
So we can use this formula, and Z here is just the atomic number, 10. So that's just the number of protons in the nucleus. And so we plug in 10 for Z, and then N is any positive whole number. And this will at least give us a pretty good approximation of the possible energy levels of that atom. Essentially, N being the energy level that the electron is at, assuming that for whatever reason, it only has one electron. So we plug in Z for 10 for Z. That'll be 10 squared is 100. So we get 13.6 times 100 is 1360. 1,360 electron volts divided by N squared. Which means we're just going to be dividing that energy value, negative 1,360 electron volt just being a unit of energy, dividing by 1 squared or 2 squared or 3 squared or 4 squared and so on. Any questions on that formula so far? So let's try plugging in some numbers and see what happens. I'll grab a calculator. First one, of course, if we just plug in 1, we're just dividing by 1, so we just get the number, negative 1360. So the lowest possible energy level, E1, is going to be negative 1,360 electron volts. And then everything beyond that, we're just going to be dividing this by 2 squared or 3 squared or 4 squared and so on. So 1360 divided by 2 squared is going to be 340. E2, negative 340 electron volts. And then 1360 divided by 3 squared is going to be about 151. I'm just going to round off to the nearest electron volt here. E3, negative 151 electron volts. And same thing divided by 4 squared. E4 is going to be negative 85 electron volts. And then same thing divided by 5 squared is negative 54 electron volts. So by the way, what's happening to the gaps between these as we go further and further up the scale? The gap between E1 and E2, E2 and E3, E3 and E4. What's happening to the size of those gaps?
They're getting smaller as they get closer
getting
to
smaller and smaller. So because E1 to E2, that's a very large gap. E2 to E3, that's a somewhat smaller gap. E3 to E4, even smaller, and so on. So if we wanted to put these more to scale, it might be something more like this. And in fact, we often draw this out as a chart looking something like this. So we've got our energy levels. These bars, these horizontal bars just represent the various possible energy levels. And then they're getting closer and closer together. We presumably are going to have an E6, an E7, all getting closer and closer together. And then up at the top, the highest possible would be 0. So somewhere up top, we've got a 0. And 0 isn't really a possible energy state because you'd have to, as n gets larger and larger, your energy level gets closer and closer to 0, but never quite gets there. So 0 is just this hypothetical maximum. In fact, if you add enough energy to bring it up to 0 or beyond, you've actually broken the bond and allowed the electron to leave the atom. But these values and on up, E6, E7, E8, those are the possible values that energy of the electron could have. And it looks like part A is just asking what's the energy difference between the two lowest energy levels. So we could just subtract those, negative 340 minus negative 1360. That's what, 1020? So this difference, this delta E, is 1020 then. Electron volts. And what that means is that if it's in the E1 state and you want to bump it up to the E2 state, you need to give it 1020 electron volts. And how would you give it energy? How do you transfer energy to an atom like this?
Photons?
Yeah, you hit it with a photon. And as long as the photon you hit it with has exactly that much energy, exactly 1020 electron volts, then that means that that photon will be absorbed and the atom gains that energy that the photon had. And what determines how much energy a photon has? What other information might you have that would allow you to calculate the energy of a photon?
The wavelength.
Yeah, exactly. If you know the wavelength, you can just use hc over lambda, or if you know the frequency, you can just say h times frequency. But either way, frequency or wavelength, basically the same information, that determines the energy that that photon has. So there's a certain wavelength and therefore a certain color of light that's going to have exactly the right amount of energy to bump this atom from E1 to E2. And then maybe a different amount of energy, a larger amount of energy would bump it from E1 all the way up to E3 in one go, or from E1 all the way up to E4. So you could bump it up from E1 up to any energy level you want, as long as the photon has the exact right amount of energy. You can't end up at some in-between state. You only have these allowed energy levels. Nowhere in between works. Any other questions on that?
So a photon is basically something an electron uses to go in between the energy levels?
Yeah, the photon is the agent of transfer of energy. So very much in the same way that, like back in 7A, we were saying the delta energy of a system equals work plus heat. The work and the heat were the processes that cause the energy of the system to change. Here we would have delta energy of the atomic system, delta E of the system equals energy of the photon that hits it. And really that should be plus or minus, I guess. Because you might have a photon striking, like a photon being absorbed by the atom and gain more energy, or you might have the atom losing energy by emitting a photon. So the delta energy of the system could be positive energy of the photon if the photon's being absorbed, or negative energy of the photon if the photon's being emitted.
Okay, thank you.
Alternatively, we could just say energy of the photon is absolute value of delta energy of the system. Because energy of a photon is always positive. It's just the amount of energy the photon has. But the system could be gaining or losing energy depending on whether it's absorbing or emitting a photon. So for delta energy of the system, that's going to depend on what system you're talking about. Different systems use different formulas for energy. In this case, we'd be using the negative 13.6 z squared over n squared formula. Energy of the photon is always going to be h times frequency or h times c over lambda, depending on which information you have. Any other questions on that so far? Then let's take a look at part B, which I think is a similar idea. We're just using different molecule, guanine nucleotides. And yeah, so in this case, I think we're talking about the same overall sort of chart in terms of energy values, but we're going to have different amounts of different values for the energy. So we don't really know what these energy values are, except it tells us that the ionization energy is 4.42 electron volts. That means if the photon that hits the molecule has 4.42 electron volts or more, then it's able to knock the electron out of the atom and make it an ion. And that's what I was talking about earlier, that if you're at some energy level and you add enough energy to make the energy go up to 0 or higher, you've broken the bond. You've allowed the electron to get enough energy to leave the atom entirely. And this is, by the way, is how solar panels work. If you've got these layers of the correct sort of material, when the right wavelengths of light hit it, they cause this material to lose an electron. An electron gets bumped out of the atom, and any extra energy becomes kinetic energy of the electron in motion. Those moving electrons form electrical current. So that's what we're dealing with here, except in this case, the molecules are part of DNA, and we don't really want them to lose electrons because that causes genetic damage. So we want to know what sort of light, what color of light is capable of doing this. In this case, though, the amount of energy the photon would have to have is 4.42 electron volts or more. We want to know what wavelength is going to make that happen. So what formula can we use to relate the energy of one photon versus the wavelength?
HC over lambda.
Yeah, HC over lambda will work. And let me go grab a lambda. Lambda is, where's lambda? There's lambda. Okay, so we can use H times C over lambda. And in this case, we know the energy the photon needs to have. If the photon has 4.42 electron volts or more, then it's going to be able to ionize the molecule. So let's set the energy of the photon equal to 4.42 electron volts. And then we want to solve for lambda. So how would we isolate lambda here?
Multiply lambda and then divide by E photon.
Yeah, multiply both sides by lambda, divide by energy of the photon. And that'll give us the value of lambda. And let's actually plug in the numbers there. What is the value, instead of using the value of H and the value of C, we can use the shortcut of just filling in, what's our usual default value for HC?
It's 1240 EV times nanometers.
Yeah.
Or, yeah.
Yeah, and that's a very convenient amount of units because the electron, the energy of the photon we already have in electron volts, so that's going to cancel out. And we'll end up with just units of nanometers, which is good because that's usually how we want to measure light wavelength anyway. So we divide these, the electron volts are going to cancel out, and 1240 divided by 4.42 is about 280, well, 281. So if the wavelength is exactly 281, the energy is going to be about 4.42 electron volts. What we want is for the energy to be, in order for this to happen, in order to ionize the nucleotides, we're going to need to have more energy, or that energy or more. So for wavelength, we should say this energy or this wavelength or more or less than that. If we want more energy, should we be using a higher or lower wavelength?
A lower wavelength?
Yeah, lower wavelength, because we're dividing by wavelength here. Lower wavelength is going to lead to more energy. So we can conclude that if wavelength is lower than 281 nanometers, then energy of the photon is going to be greater than, or I guess that should be less than or equal to. Then energy of the photon will be greater than or equal to the ionizing energy, 4.42 electron volts. So if we're using light with wavelength 281 nanometers or less, then it's going to cause ionization. And is that visible light?
No.
Yeah, that is beyond visible light, right? Visible light is what, 300 or 400-ish to 800 or 900-ish nanometers?
I think it's like 400 to 700.
Okay, yeah, so smaller than that even. So yeah, this is definitely beyond the range of visible light. It's shorter wavelength than the shortest wavelength of light that you can actually see. And short wavelength, if you look at just the visible spectrum, which end of it is short wavelength? Which color?
Red?
Red is the low,
Is that the highest?
low energy. So that's going to be longer wavelength.
Oh, my bad. So blue.
Yeah, blue violetish. So generally the red end, red light has low energy per photon. That doesn't mean that it's like weak light. The energy of a beam of light depends more on how many photons per second. But red light is low energy per photon, low frequency, and long wavelength. On the other end of the spectrum, blue-violet light is high energy per photon, high frequency, and short wavelength. And this energy we're dealing with, this photon we're dealing with here, 281 nanometers, is even shorter wavelength. So this is going to be all the way to the violet end of the spectrum and beyond. So we would call that ultraviolet light. Or maybe even more so. This might be all the way to, it's definitely not visible. It might be ultraviolet, it might be X-ray. We'd have to take a look at the chart to figure out exactly where it is. But it's definitely beyond the violet end of the visible spectrum. So ultraviolet or more so. Any questions on that?
I had a question, Casey. So since it needs 4.42 or more, I get a little confused with the or more because I thought if it's quantized, doesn't it have to be an exact number? Or are you saying that like or more would still have to be like another exact energy level?
If we wanted to end up on another energy state, another energy level, then yes, it would have to be exact. But in this case, we're not trying to bump it up to another specific energy state. We're trying to bump it up to 0 or beyond.
Oh, and we get that, is that like what the phrase ionization energy is telling us?
Yeah, ionization basically means that we're trying to kick the electron out of the atom, because the atom would then be missing an electron, so it would be positively ionized.
Okay, got it. Thank you.
Mm-hmm. And that's what I was saying earlier about how, I mean, the chart like this is basically possible energy levels if the electron is bonded to the atom. Once you get the electron up to, if you give the electron enough energy to get to 0 or higher, it's no longer in the atom, so the energy is no longer quantized. It's free to have any energy level, not just these quantized energy levels. Any other questions on that? All right, do you want to try another quantum problem or get back to some magnetic flux and induced current, or what?
I'd like to do the newer stuff. I don't know what everybody else wants.
Okay.
Yeah, the magnetic flux and induced current stuff would be helpful to go over.
Yeah.
I saw a problem above this that I think is going to work well for that. Actually, I guess 3 problems. We've got 3 situations with magnetic fields and loops of wire. So let's try each one of these individually. And let me see if I can zoom in on this. Yeah. So magnet is placed near a loop of wire, and the magnet is brought closer to the wire. And we want to know, does that cause any current in the loop? So first of all, let's take a look at the magnetic field. This magnet is going to, this bar magnet causes magnetic field in which direction in this vicinity?
Down.
Yeah, down.
In this region, it's going to be downwards magnetic field. The overall magnetic field is going to be this sort of swirling dipole shape. We're going to get these loops, but we don't really care about the overall magnetic field. We just care about the magnetic field in this general region.
Casey, can you explain how we know it's going to be down, please?
Yeah, in general, if you've got a bar magnet, like a permanent magnetic dipole, then you should expect the magnetic field to be going, at least the magnetic field outside the magnet, to be going inwards towards the south end of the magnet and outwards from the north end of the magnet.
Oh, okay, that makes sense. Got you.
And if you look at this in the big picture, you're going to have magnetic field lines going inwards towards the south end of the magnet. But they don't just stop there. They keep going through the magnet and outwards away from the north end of the magnet. And then you're going to have maybe a magnetic field going in like this towards the south end of the magnet. And this is actually going to go out of the north end and loop around, going back into the south end. Maybe not that exact shape, but something like that.
But wouldn't this be like the other session that we had earlier today where the lines don't actually go through the loop, so there would be no flux?
Yeah, the thing is the magnetic field in this region, I mean, the overall magnetic field is going to be these loop shapes. This is the characteristic sort of shape we get from a magnetic dipole. But we don't really care about the magnetic field everywhere here. We just care about the magnetic field in this region, which is going to be overall downwards. And some slanting, because it's going inwards towards the south and from all directions. But yeah, in this case, if we've got this loop oriented like this and magnetic field going straight down, the magnetic field isn't going through the loop, it's just skimming along the surface. So this is no flux at all. And of course, no flux doesn't necessarily mean no induced current. Induced current isn't about flux, it's about how the flux is changing. But if we take a look at the change here, we've got this magnetic field. The reason it's no flux is because the flux is supposed to represent the extent to which the magnetic field lines are penetrating through the interior of the loop. So for instance, if you had, so flux would be something like magnetic field going through the interior of the loop. But that's not what's happening here. The magnetic field's not going through the loop. The magnetic field is just skimming along the surface. There's no throughness to that. It's not going through the loop. It's just bypassing the loop, skimming along the surface. So that counts as no flux at all.
But you said there could be an induced current. Do you mean if there is no flux initially and then, for example, the loop rotates so that it gets all of the arrows in it?
Right.
Or like then there would be an induced current in that situation?
Or even if it's just a little bit. Like let's say we've got, right now we've got no flux, but then we rotate and now there is flux. That's a change. Yeah. If the flux is in the process of changing, even if there's no flux right now, but it's in the process of changing, so there will be flux, or if there was flux, but it has just changed, so now there's no flux. The fact that flux is changing is what causes induced current. It doesn't matter how much flux there is or whether there is flux at all. What matters is that it is changing. And that change is what causes current to flow. So what we need to check is, I mean, we know there's no flux right now. We want to know, is the flux in the process of changing? So with this loop of wire, all we're doing is moving the loop, or I guess it starts off far from the magnet. We're moving the loop of wire, or we're moving the magnet closer to the wire. So the loop stays where it is, but we're moving the magnet. But the effect is the same. It doesn't really matter if you're moving the wire towards the magnet or moving the magnet towards the wire. Moving the magnet towards the wire still means that the wire is now in a stronger magnetic field zone. So now what's the flux going to be?
There's still no flux.
Right, still no flux because the magnetic field lines are still just skimming along the surface, not going through. So this would mean, since we start and end with no flux, so that there's no overall change, no change means no induced voltage. So nothing really happens. Yeah, normal line just means a vector perpendicular to the surface itself. In this case, which direction or directions would be perpendicular to the loop of wire surface?
In and out of the page?
Yeah, we could use inwards or outwards. Usually, if possible, you want to use the normal vector that most closely aligns with the existing magnetic field. But in this case, it doesn't really matter, because if we use inwards or outwards, if this is our normal vector, so let's say we use an outwards normal vector. What's the angle between that normal vector and the magnetic field?
$90.
Right, 90-degree angle. We've got magnetic field downwards, normal vector outwards. Those are at right angles to each other. And since the angle is 90, cosine of that angle, because we define flux as area times magnetic field times cosine of the angle. But what's cosine of 90 degrees? Yeah, cosine of 90 degrees is 0. So we get area times magnetic field times 0. In other words, no flux at all. And this is still true even if you use a normal vector in the inwards direction instead of the outwards direction. It's still a 90-degree angle to the magnetic field, so you still get 0 flux. And again, conceptually or geometrically, that's because the magnetic field is just skimming along the surface and not going through the surface. Algebraically, we just plug in 90 degrees for theta, and we get that A times B times cosine of 90 is 0, no matter what the area or magnetic field is. So the amount of flux doesn't really matter. The important thing is flux is not changing here. And the fact that there's no change in flux means there's no induced voltage, and therefore no induced current.
How'd you find the normal? Like when you're deciding what the normal is, can you just briefly go over how you pick that? Like if it's right or left, or like in or out of the page? Normal literally just means perpendicular. So what you're looking for is a vector that's perpendicular to the surface formed by the loop of wire. Like I usually think of it as taking this loop of wire, dipping it in bubble soap, and it now has this, this skim of bubble soap on it. That's the surface we're talking about. The normal vector is just a vector perpendicular to that surface. So if you're holding your loop of wire like this, the normal vector is straight up or straight down. If you're holding your loop of wire like this, the normal vector would be straight to the left or straight to the right. If you're holding the normal vector like this, it would be straight outwards or straight inwards. Or if it's on some diagonal, you're going to have a diagonal normal vector.
But the normal vector is just a vector pointing straight perpendicular to the surface bounded by the loop of wire. That's what we mean by a normal vector. And this is basically the same as the normal vector or the normal line we were talking about for refraction and reflection. You can't really define an angle between a surface and a line, but you can create a line perpendicular to a surface, and then you can measure the angle between that normal line and another line. So we're creating the normal vector in the first place so we have an angle to measure, the angle between the normal line and the magnetic field, or the normal vector and the magnetic field. Any questions on that so far? And note that you always have two options for the normal vector. Like in this case, you could use outwards or inwards. Generally, what you want to do is choose the direction that most closely aligns with either the magnetic field at the beginning or the magnetic field at the end, or both. If you choose the other direction, the mathematics still works out, but you end up with a bunch of negatives that make it difficult to figure out what's going on conceptually. Because you'd end up with an angle more than 90 degrees, and cosine of an angle more than 90 degrees is negative. Negative amount of flux, again, works fine mathematically, but it becomes much more difficult to visualize what's going on. Any other questions on that example so far?
Wait, sorry, what did you mean by selecting the normal vector closest to magnetic field?
For instance, and let me put it as side view here instead. A different example. Let me just delete this example. If we're looking at a different situation, let's say we're looking at a side view of a loop held up vertically like this. So we have a loop. We're looking at this side view. So let's say this region looks thick because it's closer to you. This region looks thin because it's farther from you. Maybe I can exaggerate that even a little more. Yeah, 3D perspective in a 2D drawing. So cool. And let's say we have a magnetic field. First of all, before we even draw in the magnetic field, what are our options for the normal vector here?
Right or
Our
left?
only options for normal vector are left or right, because those would be the directions perpendicular to the surface enclosed inside. In fact, we could even draw in that surface. The surface we're talking about is again, if you just imagine dipping this in bubble soap. The loop of wire encloses this invisible surface. We're talking about a vector that is perpendicular to that surface. So our normal line is just a vector perpendicular to the surface, either to the left or to the right. And we would choose one of those based on the magnetic field itself. Let's say the magnetic field in this region is all pointing to the left. We just got, let's say, a fairly uniform strength magnetic field pointing to the left everywhere. In that case, we would want to choose a normal vector to the left also. So we've got magnetic field in green, normal vector in red. Let me label those. So we got a normal vector. We've got a magnetic field. And in this case, if you compare the normal vector and the magnetic field, what's the angle between those?
Would it be 0?
Yeah. In this case, the angle between the normal vector and the magnetic field is 0. And what's cosine of 0?
1.
Right. So that means the flux would be A times B times 1. And note that that's the largest it can possibly be. Cosine can't give you a result larger than 1. So flux can't be larger than A times B times 1. So in this case, if the normal vector is perfectly aligned with the magnetic field, note that that means the magnetic field vectors are going through the center of the loop or through the interior of the loop as much as possible. So this is the situation where you get the most flux. On the other hand, we could define, since we have the option of defining a normal vector to the left or to the right, you could define the normal vector to the right instead. However, that's not all that good an idea because although mathematically it works, now what's the angle between this normal vector and the same magnetic field?
(180).
Yeah, if you've got vectors pointing in exact opposite directions, sometimes we describe that as anti-parallel. The angle is 180 degrees. And what's cosine of 180 degrees?
-1.
Yeah, so you'd get a negative value for flux. And again, mathematically, this works out just fine. You end up with several negatives that end up canceling each other out in the end. So this does not affect the actual physical result. This does not influence, like your choice of normal vector does not influence what's physically happening. But it does make it a lot more difficult to visualize what's going on if you have negative amount of flux. So I would just generally recommend choosing the normal vector that aligns most closely with the existing magnetic field. And of course, it doesn't have to be exactly aligned with the magnetic field. Maybe the magnetic field vectors here are, maybe we've got magnetic field vectors that are not in nice, neat perpendiculars to the surface. Maybe the magnetic field vectors are more like this in this region of space. Maybe this is our magnetic field in this region of space. We would still calculate the flux in the same way though. We just take the angle between the normal vector and the magnetic field vector. So this angle right here, that would be the theta we'd use in the AB cosine theta formula. Any questions on that? And then since flux depends on those three things, area, magnetic field, and angle, if any one of those three things is changing, that could potentially lead to a change in flux and therefore induced voltage. So if the area is changing, if you're making the loop of wire wider or narrower, or if the magnetic field is changing, maybe you're moving the magnet closer to the loop of wire or further, or maybe you're moving the loop of wire closer to the magnet or further, that could be a change in flux, if there's flux at all. If the flux is zero, then it just stays zero. Or a change in angle. If you're rotating the loop of wire, then you're changing the angle between the normal vector and the existing magnetic field. Or alternatively, you could keep the loop of wire where it is, but you move the magnet around in sort of an orbit around the loop of wire, then you'd be changing the angle. So any of those three things changing could potentially result in the flux itself changing, and change in flux causes induced voltage.
I had a quick question.
Mm-hmm.
So if the wire were rotated, so it was like flat and there were magnetic field lines going through it, then would there be increased flux if that was moved closer to the magnet?
In the original situation?
Yeah, if it was like flat instead.
Yeah. So if you rotate it so it's like this instead, and you move it closer to the magnet,
yeah,
then you have flux in the first place, a little bit of flux because there's a weak magnetic field. Move it closer, we're now in the presence of a stronger magnetic field. That would mean more flux, so that would be an increase in flux, and that would cause induced current.
Okay, thanks.
Any other?
So then so then in that case, the induced current direction would just oppose that increased flux. So how would we get that direction of the induced current from that situation?
Let's say we have that situation as just described. We've got this loop of wire oriented more flat. So this sort of shape. Again, imagine this thicker end is closer to you and this narrower end. I mean, it looks thicker because it's closer to you, and this end looks narrower because it's further from you. And we've got magnetic field lines pointing overall downwards. So there's our magnetic field. And we have this surface inside the loop of wire. So we're defining this surface. That is the surface we care about. And we want to create a normal vector. So what are our options for a normal vector direction?
Up or down?
Yeah. And we want to choose the one that most closely aligns with the existing magnetic field. So let's say down. So there's our normal vector. The angle is just 0 because the normal vector and the magnetic field are in exactly the same direction. But we're going to be moving this so that the loop of wire is closer to the magnet. So if we move it from far from the magnet to closer to the magnet, what happens to the flux?
It increases.
Yeah, the flux has increased. So let's make a note of that. We move the wire closer to the magnet. Or, I mean, technically we're moving the magnet closer to the wire. But the effect is the same. The flux increases because the magnetic field is getting stronger in the vicinity of the wire. So if we want to treat that in terms of a direction, formally flux is a scalar and does not have a direction, but for practical purposes, you can treat flux as being in the direction of the normal vector. So if you visualize this as flux being a vector in the direction of the normal, so we've got, let's say this is our initial flux. Flux initial. But then the flux has increased. The final flux is going to be larger. Because we're now in the presence of a stronger magnetic field. So if you imagine the flux as a vector, which it isn't, but we can treat it as being in the direction of the normal vector as just the direction we're defining as positive. We've got an initial flux that gets stronger and stronger and stronger. That's a change in which direction?
Downwards direction?
Yeah, a downwards change. But Lenz's law says that the induced current is going to be in a direction opposite to the change in flux. So downwards change, reverse that because of Lenz's law, and right-hand rule says we get current circulating this way. So that's generally how I visualize this. Figure out the direction of the change in flux, treating the normal vector as the direction of flux. So flux is pointing downwards. In this case, it's getting stronger and stronger. That's a downwards change. Lenz's law says reverse that, use the right-hand rule in that upwards direction, and we get current circulating this way, which I would interpret as counterclockwise when viewed from above. So this direction of circulation, if we actually draw this on the diagram here, is going to look something like current going this way.
Wait, can you go over how you found the current again?
Yeah, the change in flux is in the downwards direction. Lenz's law says the current is going to be, the induced effect is opposite to that. So downwards change in flux means upwards induced effect. Curl your fingers of your right hand. So point your thumb of your right hand upwards because that's opposite to the change in flux. The curl of your fingers tells you the direction current is circulating. So that's going to be circulating this way. And if I were to describe that in words, I would imagine looking at it from above and say, that's going opposite of the direction of the hands of a clock. So that is counterclockwise when viewed from above. Or you could imagine looking at it from below and say that's clockwise when viewed from below.
Casey, sorry, do you mind like maybe doing another example? Because like, I don't know the induced current and like the different directions. I'm still kind of confused on how you find that.
Yeah, I mean, in all the cases, it's going to be figure out the direction flux is changing, take the opposite of that direction, and point your thumb in that opposite direction, and the curl of your fingers tells you the direction current's flowing. But yeah, let's try out the other examples and see if we can apply the same concept.
So like for this one, flux is changing downwards because it's getting larger.
Yeah, we've got it. I mean, the flux is, the normal vector is downwards. So we treat the flux as if it's in the downwards direction. A downwards vector that's increasing is a change in the downwards direction. On the other hand, if it were downwards and getting weaker, we treat that as an upwards change. Because if it's pointing downwards and getting weaker and weaker and weaker, that's changing in the upwards direction. So you want to figure out the direction of delta flux, the direction of the change in flux. Take the opposite of that as the direction of the induced effect, and then use the right-hand rule applied to that to figure out the direction current is circulating.
Could you also say for this example that initially before you moved it, the current would or the magnetic field would go in the same direction, like downwards, so then that current would have to be clockwise, and then since it's strengthening as you move the whole thing down, you would want an induced current to oppose that, so then it would have to go counterclockwise?
In this case, yes. I'm not sure that's always really going to work, though, because sometimes you might be dealing with a case where there is no magnetic field to start with. And also that gets a lot trickier if you're dealing with changing angles. But the general idea is that you can always use the idea that if you treat flux as being in the direction of the normal vector and look at it as, is flux increasing or decreasing? And then establish a direction associated with the delta flux.
All right, thanks.
Casey,
yeah.
Sorry, don't mean to interrupt. I just had a quick question. So when you're like saying clockwise or counterclockwise, you have to be specific with saying like your perspective, right? Because I heard you saying like looking at the top, like you have to be specific with that.
Right. Because if you're looking at it from the top, it's counterclockwise. If you're looking at it from the bottom, it's clockwise. This does require a point of view.
Okay.
The only exception is if you're talking about a loop that's in the plane of the page itself and you don't specify a perspective, then it's just assumed that it's from the perspective of somebody looking at the page.
Okay, that makes sense. Thank you.
But any sort of 3D stuff, like if it's in the plane of the page, presumably we're defaulting to from the perspective of the viewer. If you're talking about any other orientation though, you have to specify, are you looking at it from this side? Are you looking at it from this side? Or if it's arranged like this, are you looking at it from underneath or from above? Because those are going to make a difference in terms of the actual direction.
Sorry, just one more quick question. From what you just showed with the loop right there, would you say you're looking at it from the left or from the right when you were holding the loop up kind of vertically? Yeah.
Like this, yeah, you could look at it from the left or from the right.
Okay, thank you.
You can sort of tie that into the normal vector. You want to be looking at it from the direction the normal vector is pointing or from the other direction. You just want to specify which one of those directions you're talking about. All right, so let's take a look at B then. We're going to want to know a magnetic field and a normal vector and what's happening to the flux. So I will keep those. I think we can get rid of the rest. So we've got our loop of wire. The small loop of wire is what we care about. If you think of the small loop of wire as the test object, and then we've got this larger loop of wire that's being powered, you can treat that as like the source current. So our surface that we're talking about is just the surface enclosed inside this smaller loop of wire. That's the area in the area times magnetic field times cosine theta formula. And that means what are our options for a direction of the normal vector?
In or out?
Yeah, our normal vector could be inwards or outwards. And we'll choose one of those based on the existing magnetic field. We know we have current, to start with, we have current circulating counterclockwise. That current, that powered current in the larger loop is going to create magnetic field in which direction?
Out of the page?
Yeah, we've got this outwards magnetic field based on the loop variant on the first right-hand rule. Curl your fingers in the direction current is circulating, and you get an outwards magnetic field. So outwards magnetic field everywhere in this region of space. Make a thicker line there. So this entire region inside the big loop has outwards magnetic field. And in particular, in the middle, it also has outwards magnetic field. What I would do here for the right-hand rule is actually curl your fingers in the direction current's flowing. So from your perspective, you're seeing current circulate like this. Curl the fingers of your right hand in the direction current's flowing, and your thumb tells you the direction of the magnetic field interior to the loop. So it's a variant on right-hand rule number 1 that works specifically for the magnetic field inside loops of current. Because loops of current always form a very predictable magnetic field. You're going to get a very strong magnetic field in the middle with direction given by that variant of the right-hand rule. And then outside the loop, it's going to curl around. You're going to have a weak magnetic field outside the loop in the other direction. In fact, it forms a dipole. You've got magnetic field, strong magnetic field inside the loop, curling around outside the loop and bending back in. So it's that dipole sort of fountain shape. So a loop of wire is an easy way to form a magnetic dipole without having to have a bar magnet. It's also controllable, which is very convenient. You have a magnetic field whose strength you can control just based on how much current you're running through the wire. So this is how you would make an electromagnet, for instance. So let's say we establish a normal vector that is in the direction of the magnetic field. Because our options are outwards or inwards, let's just choose outwards so it matches up with the existing magnetic field. So there is our normal vector pointing straight out of the page. So would you say you currently have a lot of magnetic flux or a little magnetic flux or no magnetic flux or what?
Quick question about the direction. So you did use the right hand rule and then your thumb told you which way the magnetic field is. Is it wrong if we used our thumb going in the direction of the current and then our fingers pointing out towards us tells us the magnetic field?
Yeah, that would also work. You could say, like, let's say if you look at a specific section of the wire, like let's say you're looking at the top of the wire, on top of the wire, magnetic field, or the current is pointing to the left. So you point your thumb to the left, curl your fingers, and underneath you get an outwards magnetic field.
Yeah. Okay.
Or if you look at the bottom of this loop, you've got current going to your right. Curl your fingers, and above you get magnetic field outwards. So no matter where you put your thumb for current, as long as you're pointing it in the right direction, you get outwards magnetic field in the center.
Okay.
But as a shortcut, if you're dealing specifically with a loop of wire, you can just curl your fingers in the direction current is flowing in the loop, and your thumb tells you the direction of the magnetic field. Same result, just a useful shortcut if you're specifically dealing with a loop of wire with current flowing through it already. Any questions on that so far? All right, and so the initial flux, since we have the normal vector and the magnetic field pointing in the same direction, what's the angle there?
0.
Right, and cosine of 0 is 1, which is the largest it can be. So the initial flux is large, A times B. That's a large amount of flux.
There's flux because it's going like directly through the wire. Because you're holding the wire like, I don't know how to describe, like you're holding the wire right in front of your face, flat, and then like the flux is going in and out of that wire.
Yeah, conceptually, we're looking for to what extent is the magnetic field vectors piercing through that surface inside the loop.
Yeah.
So in this case, we've got the loop, we've got magnetic field going straight out, and that magnetic field going straight out is definitely going through the interior of the loop.
Yes.
That's lots of flux.
Perfect, thank you.
And I think that's a great way to visualize it. Even if you just got like make a loop with your fingers and point a pencil in the direction of the magnetic field and ask yourself, is that pencil going through the interior of the loop, or is it just skimming along the surface? That's a good idea to get a conceptual visual idea of what flux is. And is there flux or is there no flux in that situation? What about after? What are we doing here to make things change?
Are you basically like expanding how big the wire is?
I don't think we're changing the shape of the wire here. What is it?
You're changing the current.
Yeah,
Oh,
the current.
so it reverses.
So we're messing around with the power supply to make the current, because this powered loop, we can control the amount of current in that. So we're changing this, presumably, I mean, of course, this is not going to be an instantaneous change. We're going to take lots of power and then presumably make that power weaker and weaker and weaker down to 0, and then start applying power in the other direction to make current flow the other way. What's that going to do to the magnetic field?
It'll change it to be into the page.
Right. We're going to have the opposite direction magnetic field. It'll be into the page instead of out of the page. So we're going to have magnetic field vectors pointing inwards instead of outwards. So the final magnetic field is going to be inwards vectors because we're changing the direction of the current. We don't want to change our normal vector though. You don't want to change your coordinate system halfway through the problem. So we're going to keep the same normal vector. At this point, what is the flux?
It's 0 because the angle is 180.
And what's the cosine of 180?
0.
Cosine of 90 is 0. But yeah, cosine of 180 loops all the way back to -1.
Oops.
So if we actually plug in 180 for the angle, flux final equals -a times b, because cosine of 180 is -1. So we end up with negative flux. And that's going to be kind of weird because we end up with a flux essentially we end up with magnetic field piercing through in the opposite direction. But let's focus on the idea of change. If we're changing from a positive amount of flux to a negative amount of flux, does that count as an increase or a decrease?
Decrease.
Yeah, flux has decreased. So if we reverse direction of current, the direction of the powered current, the flux has decreased, changing from positive to negative. So if we got a decrease in flux, we can actually associate a direction with that. And this gets kind of confusing if you try focusing on the magnetic field, but stick with the normal vector and it should be okay. If we treat flux as being in the direction of the normal vector, we start with a strong outwards amount of flux, but it's getting weaker and weaker and weaker and weaker. In fact, it's even changing direction altogether. So, but let's focus on just the beginning. It's pointing outwards, it's getting weaker. That's a change in which direction?
Into the page.
Right. A decrease in an outwards value is an inwards change. So delta flux is an inwards vector. So delta flux is inwards. Yeah, and numerically we would say delta flux is a negative value because formally flux is a scalar, not a vector. So delta flux is a negative value. But for practical purposes, you can treat flux as being in the direction of the normal vector. So we can say that in terms of direction, delta flux is inwards. Flux was an outwards vector, but since it's decreasing, that's an inwards change. But again, Faraday's law has a negative in it, so we have to reverse that direction to find the induced effect. The change in flux is inwards, so the induced effect is outwards. And you can curl your fingers to figure out what that effect is going to be in terms of a current. Outwards induced effect, curl your fingers, that's the direction current is going to flow. So it looks like current is going to circulate. I would call that a smaller arrow for one thing. We're going to get current circulating counterclockwise in this inner loop. Any questions on that so far?
Casey, could you repeat? I don't really get like why changing the direction decreases the flux. Like, how does that change it? Like, it's just changing it from positive to negative is what decreases it?
Yeah, a negative value is less than a positive value. So if it's negative, that's a decrease.
Okay, and it's negative just because it's going the other way?
Yeah, because based on the direction we defined for the normal vector in the first place,
okay.
The angle started off at 0 degrees because the original magnetic field was in the same direction as the normal vector. And the final situation has the magnetic field in the opposite direction from that same normal vector. So the new angle is 180, and cosine of 180 is -1.
Got it. Okay, cool. I just missed that. Thank you.
Mm-hmm. You could also look at this in terms of as a gradual process, because it's not like the magnetic field is instantly changing from outwards to inwards full strength. It's going from outwards full strength to a little bit weaker, a little bit weaker, a little bit weaker, eventually no magnetic field, and then creating a little bit of inwards magnetic field and a little more, a little more, a little more, eventually getting to full strength. So if you look at just the first short period of time, you've got a strong outwards magnetic field that's getting a little bit weaker. That's a change in the inwards direction. Inwards change, reverse that for an outwards induced effect, and the circulation of your fingers tells you the direction current is flowing.
Got it. Thank you so much.
And yeah, you could certainly think of it numerically, just in terms of you start with a positive value for flux, you end with a negative value for flux, that is a decrease in flux. Any other questions on that?
Yeah, I had a quick question. So like when I started doing this problem at first, I put the normal as being going out, or sorry, going into the page.
Mm-hmm.
And so then I had a negative value of flux in the beginning.
Mm-hmm.
And so is it always just better to make the normal being in the same direction as the magnetic field? Because I got like an increase in flux in that way.
Well, that actually also works. If you think of the normal vector as into the page, but it's increasing because you're going from negative to positive. So you get a little bit inwards and more and more and more inwards. So that means if it's inwards and increasing, that's an inwards change. So the induced effect is going to be opposite to that. So you still get current circulating in the same direction. So you end up with the current, I mean, the physical result is the same no matter which normal vector you choose.
Mm-hmm.
I would say it's usually going to be easier if you choose a normal vector that aligns with the existing magnetic field. In this case, the magnetic field is changing direction, so you could use either one. I find it's usually easiest if you choose the normal vector that aligns with the original magnetic field if possible. But again,
okay.
It works. It's just a matter of which one's easier to visualize.
Okay, thank you. That makes sense.
Any other questions on part B? Okay, let's take a look at C and look at how that's different. So we have two infinitely long wires, and we're making the current weaker. Let me copy some of this over. Oh. Don't need a normal vector that big. Okay, get rid of that. And we'll see what's different here. So we've got a loop of wire. We're defining a surface enclosed within it. And again, we have normal vector options inwards or outwards. First of all, though, let's find the B field. What can you say about the magnetic field caused by these two wires?
Would it be out of the page?
From which one?
The right one?
Yeah, the right wire, again, using the usual right-hand rule. Upwards current, curl of your fingers tells you the direction of magnetic field. The right wire is going to cause outwards magnetic field in the region of the loop. So we're going to get outwards magnetic field from the right wire. What about
the left? Oh, sorry, go ahead.
Yeah, the left wire is going to create magnetic field into the page.
So would those two like cancel out in a way, or?
Yeah, at least in the exact center they will. Because in the middle, we're going to have outwards magnetic field from one wire and inwards magnetic field from the other wire. Equidistant and equal currents means we're going to get exactly the same amount out and in, so they cancel out. So the magnetic field in the center is 0.
So when we're finding the magnetic field, are we using the center as like our reference point?
Yeah, because we're assuming the loop of wire is in the center. If you're closer to one wire or the other, then they don't cancel out because one of them is going to have a stronger effect than the other. But we're talking about a loop of wire that's in the center between these, so the magnetic field in the center will cancel out. And since there's no magnetic field, it doesn't really matter which direction normal vector we use. So let's just choose a direction, let's say outwards. So initial flux is 0. No flux to start with. Initial flux is 0 because magnetic field equals 0. And then how are we changing this? What are we doing?
The current carried by the wires decreases.
Yeah, so we're going to take both wires and make their currents weaker. What does that do to these magnetic fields?
Would they also be weaker?
Yeah, so we get these strong magnetic fields that cancel each other out. We're going to make them weaker. And now what do we have?
The same thing, because they would cancel out again.
Yeah, previously we had strong magnetic fields that cancel each other out. Now we have weak magnetic fields that cancel each other out. So we still have no flux to end with. Flux final is still 0 because the magnetic field is still 0. So we start with no flux because the magnetic fields cancel out. We change the currents, the magnetic fields continue to cancel out. So how much is the flux changing?
It's not changing, so there's no induced current.
Exactly. No induced current, no induced voltage because there's no change in the flux. Any other questions on that one?
So the magnetic fields cancel out only in the center, not on the sides, right?
Right. So if you, I mean, we've been treating the loop as if it's occupying only the exact center. Realistically, if you spread out a little bit to the left and a little bit to the right, the left half of the loop is going to get more magnetic field in one direction, but the right half of the loop gets more magnetic field in the other direction. So overall, those end up canceling out and you still get 0 flux.
But if it was closer to the right wire, for example, then it wouldn't be a net of 0, right?
If you had your loop of wire like over here, closer to the left wire, then you're going to have more inwards than outwards. So you would have a non-zero amount of flux. And then when you change the currents in the wires, the magnetic field would get weaker, so the flux would get weaker, and that would lead to current flowing in the wire. In the loop, I mean.
Is induced current and voltage the same thing?
They're proportional, but they're not the same. Voltage is the electrical push. Current is how fast the electrons are actually circulating or flowing in terms of charge per second. And the relationship there is the usual Ohm's law that we looked at in 7b. That because you can treat the wire loop as having resistance. Ohm's law, delta voltage equals negative I times R. We can ignore the negative here because that's just about direction, but the amount of voltage difference equals the amount of current times the amount of resistance. So if you want to solve that for current equals delta V divided by R. In this case, delta V would be the induced voltage, R would be the resistance of that entire loop of wire, and then I would be the current circulating in it. So they're proportional, but they don't mean the same thing. Delta V is the amount of electrical push. It's basically the electrical version of pressure. And current is how much charge flows past a point on the wire per second.
What happened to the negative value?
The negative would be there, and I'm just basically just treating it as absolute value for now. Current, or absolute value of current, equals absolute value of voltage divided by resistance. So the negative sign is basically signifying direction, the idea that current flows from high voltage to low voltage. But in this case, we don't really need to worry about that because we can establish a direction of flow based on Lenz's law, the idea of looking at the reverse direction from the change. But the amount of current is going to be the amount of induced voltage divided by the resistance of the loop.
I guess I'm still confused about how you said there would be an induced current if it was closer to the left, because I understand that there would be a net like direction, there wouldn't be cancellation, but like how does that result in the induced current?
Because you'd have, if it's closer to one wire, that means there is flux. The reason we got no change here because the flux is 0 and stays 0. But if you're closer to one of the wires, that means there is magnetic field, and therefore there's non-zero flux. And with some flux and the magnetic fields, or the current's getting weaker, as the current gets weaker, what happens to the magnetic field?
It also gets weaker.
Right. And that means that the flux through this loop is changing. In the middle, we have 0 magnetic field and it stays at 0. So there's no actual change in flux. But if you're closer to one of the wires, if you're off center, there is a magnetic field and that magnetic field is getting weaker. So you start with lots of flux and then you end up with less flux. That changes, there is voltage.
So then what direction might the induced current be in that situation?
Well, let's check. If we're closer to the left wire, we're going to have inwards magnetic field. So we've got an inwards magnetic field. Meaning we may as well also choose an inwards normal vector. And is the flux getting stronger or weaker?
Weaker.
Weaker. So we got an inward, if we treat flux as inwards, but it's getting weaker and weaker and weaker, that's a change in which direction?
The outwards direction. So the induced would be inwards also, and that would be clockwise?
Yeah, exactly. So an outwards change reversed is an inwards induced effect. Inwards induced effect, so point your thumb in the inwards direction, curl your fingers, and you should get a clockwise current. So that's going to flow clockwise there.
Thank you.
Mm-hmm. Any other questions on that? Or any other questions before I go? I'll go ahead and post this right afterwards. You're welcome. So feel free to review any of the old videos of the workshops on YouTube, and I'll also have office hours Monday morning and Tuesday morning and afternoon. So you're welcome to come to those if you have any last minute questions. Email me over the weekend if you like. Good luck on finals. Yeah, you're welcome. Glad I could help out. And I'll continue having office hours later in the week, so feel free to stop by if you want to let me know how the final went.
Thank you.
Good luck on finals. Have a good break, and I will see you later.
Thank you.
You're welcome.